When solving any type of ML problem, whether it's for work or just for fun, I often find that when I reach the step of experimenting with different combinations of models, features, and hyperparameters, things get chaotic super quickly. My Jupyter notebook or Python script becomes basically unreadable, and I enter the pit of despair. Luckily, there are tools that can help us better approach this type of experimentation in an easy and organized way. Hi folks, I'm Trent, a professional data engineer for 6 years, and in this video I want to take you through the skills and tools needed for what I believe is one of the most underrated skills in data science and machine learning engineering, and that is hyperparameter searching and tuning. In this video, we'll go through the different levels of maturity in hyperparameter searching and tuning, from what even are hyperparameters all the way to using frameworks like Optuna. As a bonus, at the end, I'll go through a workflow that I've been experimenting with the Optuna kind of framework, just to show you what I've been thinking about and what I've been using to try and optimize my workflow. Really, the stars of this video are going to be the techniques like grid searching, random searching, and then using Optuna in Python. Now, to frame all of this in the video, I want to use a dataset and problem that I used in a previous video on linear regression. If you want to, you could go and check it out, maybe. This is using the AutoMPG dataset from the UCI ML repo. If you haven't seen the video, no worries, but I'm not going to do the in-depth analysis of the data like I did in that video. I'm just going to focus on the hyperparameter kind of searching and tuning side of things. What I want to emphasize though is that these types of techniques, this kind of like searching around, trying different combinations of models, etc., it is not a substitute for thorough data analysis prior to any type of data modeling. Preaching out of the way. With all that said, let's get started with some setup. All right, jumping into VS Code over here, I will leave a link to this repository in the description below if you do want to follow along. And as mentioned, I am using the AutoMPG or automobile miles per gallon dataset for this demo. I'll also include it as part of the repo in the data folder over here because it's really small and can kind of fit nicely into the repo, so you don't have to kind of go and download and unzip and do all of that kind of stuff. This will just work out of the box. And just to kind of give a high level of the dataset, like I said, not any in-depth analysis over here. Effectively, it is a list of cars, basically, different vehicles with their statistics, most notably their miles per gallon or fuel economy over here. I'll leave a table of descriptions of the different variables in the repo itself in the README file. I did kind of assume what the different units are. I explained that, the dataset didn't come with any units, so I had to infer what the units are, etc. But really, it's just different statistics of cars, things like the engine displacement, the number of cylinders in the engine, horsepower, weight, acceleration, etc. I also wanted to note that I am using Python 3.10 for this project. The packages that I'll be using are pandas, scikit-learn, numpy, the kind of usual stack, and then the dark horse, of course, being Optuna. I'm going to put all of these in this requirements file over here, so if you do want to follow along, you can simply go ahead and do a pip install -r requirements, not readme, requirements.txt, and you will match the exact stack that I'm using down to the version, basically, just to make things easier for you to follow. Now, before I jump into things, I am going to assume that you have been exposed to some level of machine learning using scikit-learn and pandas, these kinds of things. Nothing too in-depth, but you've at least seen it and you're familiar with like the high-level terminology. If you aren't, I do have a bunch of videos that go through things like that, but this video is mostly going to be focused on the kind of hyperparameter tuning and searching side of things, and I'm going to kind of glean over some of the details of what I'm doing. Okay, cool. Let us go ahead and try out the notebook. All right, first things first, let's do some basic imports that we'll need. I'm going to be using, as I said, pandas and numpy, and then a couple of modules from scikit-learn, the standard scalar and a shuffle split over here. We'll use these in a few, and it'll become obvious why I need these. So let's first run our imports, and then let's go ahead and read in our data into a data frame. Over here, I'm using FWF, or fixed width format. That's the kind of data that we're dealing with, and I have to manually specify the column names over here because fixed width format, or this fixed width format data, does not have the column metadata included in it. You have to manually specify it. So just going to go ahead and run that. And this gives us our data set. So you can see our variables around here, all the way up to the car names. And over here, you'll notice that horsepower is listed as a object or string type value. That's what this A means. Yeah, there you go, object. And the reason it's doing that is because of the missing values in it. They are denoted with a question mark character. And so Pandas is interpreting this as a object type. So I'm just going to go ahead and clean that, as well as remove these annoying quotes on the car names. We're not really going to be using the car names, but I kind of just copied and pasted this from the code that I used for my previous video. But yeah, it was kind of bothering me. And then further, what I'm going to do is also remove the null values completely. We're not going to deal with those in the horsepower column. It's the only column that is missing data. I'm just going to totally drop those and ignore those for now. I think there's only about 6 values that are missing from horsepower, so nothing too drastic. And that's all I'm doing over here with this cleaned df piece over here, basically creating a copy of our data frame, replacing the question marks with NaN values, converting horsepower to numeric, then cleaning up the car names as well by removing those annoying quote marks, dropping the null values, and then returning our cleaned data frame. All right, things looking better. And we can see horsepower is now a float 64. And the car names look a little nicer. Then what I want to do is apply scaling to my data. For this demonstration, I'm going to be using ridge regression, and ridge regression is affected by the scale of your data. So it's a good idea to apply a scaler. You can use kind of min-max. I just kind of somewhat arbitrarily chose the standard scaler, but that's what I'm doing over here. I'm first taking the numeric columns over here, so everything except for the car name, then applying the standard scaler to it, and then converting this back into a pandas data frame. So when you apply the scalar, it will return a NumPy multi-dimensional array, or a NumPy array. And we don't want that. I actually want this to remain a pandas data frame. So that's what I'm doing over here. Let's run that. And this will apply standard scaling. So basically convert this or map this to a normal distribution with a mean of 0 and standard deviation of 1. Then I do need this cross-validation splitter over here. So I'm going to be using cross-validation, and I want to be able to control the different subsets of data that I'm going to be working with. If you aren't familiar with cross-validation, I can make a video on that at some point, but effectively, just to explain it at a high level, I'm basically going to take the full data set and split it into 5, in this case, 5 equally sized partitions, or as close to equal as possible. And then in those subpartitions, further split the data into a training and test set for our algorithm training, basically. So each of the 5 subsets of data will have a test set, part of them, that comprises of 20% of the data. So that's what this is doing over here. And this is a shuffle splitter that comes from scikit-learn that allows you to do this. I've also specified the random state as 42 over here, just setting the random state to a number so that we get consistent results. All right, so I'm going to use this throughout, so I just wanted to set this up in the beginning. Okay, with the setup out of the way, let us go ahead and start with the very first level of maturity, which is what even are hyperparameters? Kicking things off, I basically want to import our model that we're going to be using, so that is ridge regression over here. And then also use the cross-validate function over here. So this will allow us to perform cross-validation quite conveniently on top of our different cross-validation split of data that we did earlier. So let's do these imports, grab these. And what I'm going to start with is some selected features over here. I am arbitrarily going to choose weight and cylinders. So these are our predictors. And our target variable is actually going to be horsepower. So this is what I used in a previous video and worked out quite nicely. So I'm going to use horsepower again. Just a note that typically with this data set, what actually gets predicted is the miles per gallon feature. But in this case, I'm going to be using horsepower as the target value. So over here, I'm just setting up our predictors. So I'm going to call that X. So our set of predictors comes from our scale data frame and selecting our selected features. So weight and cylinders over here, creating a copy of this to kind of disconnect the data frames, like have isolated data frames. And then the target value is going to be horsepower over here. So a single column or a single series from pandas. So let's go ahead and grab those. And then the typical kind of workflow over here for this level of maturity is that you kind of select your model. We are choosing ridge regression because, well, it's kind of a linear problem that we're dealing with. And I think that we should have an alpha value of 2. If you're unfamiliar with ridge regression, that basically determines how much kind of biasing you want away from the training set. Higher alpha means you want higher bias away from the training set so that you don't overfit your data, etc. But basically, the workflow goes something like this. You've chosen a model, right? In this case, ridge regression. You've chosen some parameters over here to enter into the model. So you kind of guesstimate an alpha value of 2 is reasonable. You derive this from all the analysis that you've done prior and think to yourself, okay, you know what? I'm going to test this out or try this out and see what I get. So we set up our model and then using, I actually don't need to reset up my CV splitter, I've already got it. Then I just need to apply my cross-validate function over here. So this is going to do the kind of training and testing loop that you typically do in machine learning. Train your data, produce a test result, and produce a score. And in this case, I'm doing things at a very high level. I'm handing it the model. I'm handing it my input features over here, my X values, and my target over here, Y, and giving it my cross-validation splits over here that we set up earlier. And by default, what this is going to use is the score of your model. So every model in scikit-learn has its own score. In the case of ridge regression and most of the linear models like ridge or lasso or ordinary least squares, it is the R² coefficient, right? And that's exactly what's used here. And just at a high level, we want R² to be as close to 1 as possible, because that indicates that a lot of the variance in our data is explained by our model, i.e. our model fits well. So that's what we are going to get out of the cross-validation over here. It's going to go through the training and testing loop for us. By default, we don't have to think about that. And it will do this over the 5 different splits and produce a set of results. I'll print those out in a second. So if I go ahead and run this, and then let's just take a look at CV results. This shows us a fit time, and we will have 5 different fit times for each of our cross-validation sets, a score time, how long it took to actually score the model, and then an actual test score. Now, as mentioned, it's using the default score of the model, so these are R² coefficients that we're reading over here. So we can see that we get like 0.79 or 79% of the variance explained on the first cross-validation set, then about 78, then 69%, 79 again, and 84.9 or about, 84, 0.849, which is about 85%. So these are the 5 different results we get from our train test splits in the cross-validation splitter. Now, actually what I want to print is the mean value. And now printing out the average test R2 score. And so this is specifically for the testing sets, right? On the testing data, you typically look at this to see how well your model generalizes and that kind of thing. You can also get your training set scores as well. You can just kind of specify that in cross-validate. I believe it is return train score over here. You can set this to true and also get your training score if you're interested in that. But really, this is your typical workflow. Basically, you've selected your features, your model, and entered in the alpha value over here and gotten your results. And at this level of maturity, you basically are done. You kind of walk away and say, well, we got 78%, or the R2 score is 0.7837, and that's good enough, and we're done. However, I know that you guys are more ambitious than that and are saying, well, what if we tried some different things, right? That's the immediate reaction after your first experiment. You kind of say, well, what if we tried different alpha values, for example? And by the way, if we look at ridge, what else can we tune? Like there's things like tolerance and things like fitting an intercept, all these different types of parameters that you could try out. Even at a meta level, you might be saying, well, what if I tried different models? What if I tried different sets of features with those models? There's a whole bunch of thoughts probably racing through your brain. So the first thing I want to do is kind of give a definition of hyperparameters before we move on to the level 2 of maturity. So what I've specified here is kind of talking to that point around wanting to try and experiment with different values, these being the hyperparameters. So to give these kind of a somewhat loose definition, The hyperparameters are the values that you, as the data scientist or programmer, explicitly feed into your model. So for example, the alpha value. Whereas parameters, or when people just refer to parameters full stop, these are the values that are determined by the algorithm you are using. So for example, using ridge regression, it is looking for coefficients to the straight line that you're fitting to your data. Those are the parameters, whereas the hyperparameters are the things that the algorithm itself uses to train. So without further ado, we move on to level 2 of maturity when it comes to tuning hyperparameters, and that is manually tuning them. Basically, we ask the question, what if we tried different values of alpha to see if the R-squared score improves as a result of us changing the value? So you kind of move on to this next stage where you now have different models. You can set up model 1, 2, and 3 over here and try different values of alpha. So we try alpha equals 1, alpha equals 0.5, and alpha equals 2. Now you could go ahead and run cross-validate 3 separate times in order, but I'm just going to write a simple loop to do exactly that. So what we want to do is iterate. So for model in, and then we can list out our models over here. So model 1, model 2, and model 3. And for each of these models, we can then do our CV results over here. So we can get our cross-validation results, use cross-validate exactly as we were using before, basically. Feed it the model, feed it the X data, the Y data, and the cross-validation splitter. So CV equals CV splitter over here. And with that, we can go ahead and print our results all over again. Okay, and then we can go ahead and run this. So we can now get 3 different results with 3 different values of alpha to see what happens to our R2 score. All right, and we can see it's kind of not much, really. All of them are sitting at about 0.78, with the final one, so model 3, doing slightly better, getting a score of 7837, as opposed to these getting 7836 over here. So slight improvement when we increased alpha. Now, again, we are stuck with the question, could we do better? And could we do better by trying out not just alpha, but what about these kind of tolerance values over here? And what about fitting an intercept versus not fitting an intercept? And what is the solver thing as well? We could try different solvers and see what that does. Now, the problem is if we try different values of, let's say, tolerance, and we want to try 2 different tolerances, we would actually need 6 different models here, because you want to try your 2 different tolerances with each of your 3 existing models. And then further, if you wanted to try the fit intercept side of things, that's another multiplier of 2, because that can be set to true or false. So then you end up with 12 models, right? And so on and so forth, right? You keep getting this exponential increase in the number of different combinations of hyperparameters that you want to try, and you'd need to go and manually configure all of those. And this leads us really nicely into level 3, basically searching through different parameter combinations. The thought that we have at this point is, if only we could easily and systematically go through each of our parameter combinations. Now, for this, I'm going to be using GridSearch and random search that comes from the sklearn library or scikit-learn itself. But before that, I want to take you through some of the theory just so that this is solidified in our minds. Okay, so basically what I have set up over here is a visual representation of what we're going to do with the grid search and random search strategies. So effectively, if you imagine an axis like this, or a set of axes like this, basically you have the parameters alpha and the parameter of tolerance over here. The grid search is basically going to set up these different combinations of the various parameters that we are talking about, the different combinations that we have set up. So what we were discussing just before is that we are thinking about, like, okay, what if I want to bring in multiple different parameters and then think about all their different combinations? This is just a visual representation of that. So if we start off with, like, say, an alpha of 1 and a tolerance of 0.001 over here, this would be one option, right? And then similarly, an alpha of 1 and a tolerance of 0.003 and 0.006. Now, this isn't to scale, right? It's we're not going to actually be using these values. This is just for illustration purposes. But effectively, you have these different combinations for each of the options, right? So we've got 3 per parameter or hyperparameter that we're talking about. So we have 9 different combinations on our grid. And this is where the name GridSearch comes from, is the fact that now we have a grid of values to search through. Now, what I have on the side here is a 3D plot, and this is going to be tricky because my 3D drawing skills are not great, but that's okay. So our grid is basically on the ground over here. So here are our 9 different values, 9 different combinations of alpha and tolerance. And up here is our R squared, and we're looking for a maxima. So perhaps our R squared plot or actually looks like this in real life. So like the actual value looks something like this, mapped out, like, you know, maybe we, assuming we knew exactly what R squared looked like, this is what the R squared function would seem to be, right? Or what it would look like illustrated on a 3D plot. Now, if we try the strategy of grid search, this is what we are doing. So let's use green for this. So grid search in this case. So for grid search, we want to go through, or it is going to go through each and every combination that we have. So all 9 of these dots, it's going to search through them and use them with our ridge regression model. So in our case, we've chosen ridge regression and we're trying different values of alpha and tolerance. So let's say we start over here in this corner. So that maps to this guy over here. What grid search CV, actually, grid search cross-validated is going to do is it's going to try this combination out and map out the R squared value that we get. So it will check what R squared value you get. In our case, we are using cross-validation. So it will probably take the mean R squared value and map that out. So this is actually a plot of the mean R squared in that case. But effectively, it's going to choose this combination and see what R squared value we find. And then it's just going to go through each and every value and do that over and over again. So just coloring these in. It will try every single combination and map out values on R squared over here and try these out. And maybe it lands up with probably this guy as the maxima, saying that this combination in the corner, so this combination over here, turns out to be the best possible fit for our model and for these hyperparameter combinations. Now, this isn't our only option. We also have something called random search because, well, you can see just on this 3x3 grid, we already have 9 different models to try out. And, you know, if we extended these out to more practical values, we'd end up with probably hundreds, if not thousands, of these dots all over. And if we had multiple parameters, this would become like a hyperplane in hyperspace that we can't see with many dimensions, but you get the idea. A grid search is really taxing, right? It takes a long time to iterate through all of these different combinations. So we also have available to us random search. Random search CV, right? So also cross-validated. And what random search does, and you can probably tell by the name, it'll start with basically a random selection of these combinations. So as opposed to iterating through all 9 of these, it may choose, let's say 3 in this case. So it'll choose these diagonal ones randomly. So choose that one, and that one, and map these out on R squared over here, right? So in this case, you know, maybe it gets to this point, but we have now not had to go through every single combination of parameters to get pretty close to the maxima over here. We've tried a subset of the hyperparameter combinations and gotten to a pretty decent guess as to what the optimal combination of parameters are. And that is effectively how a grid search and random search works. So with the theory in our minds, I'm going to go ahead and import the GridSearch CV and randomized search CV from scikit-learn. So the CV part of this just stands for cross-validation. So we're going to be performing grid search and using cross-validation under the hood. This is kind of why I included cross-validation as part of the other levels of maturity, because this was going to take advantage of cross-validation, so I wanted to use that prior. But anyway, let's go ahead and import these modules, and let's go through grid search first. So in this case, to actually form our grid or our search parameters, we want to use a dictionary, or we need to use a dictionary over here. So I'm going to set this up as a variable called params. And over here, I've specified all the parameters that I want to search through for the ridge regressor. And in this case, it's alpha, whether or not to fit the intercept, the tolerance, and the solver. So those are the names of all the different hyperparameters that I want to fine tune. So in the case of the alpha value, I am using numpy.linspace or linear space over here to create a linear array from 0.5, the value of 0.5, all the way up to 5. And I want 20 values in between these in a linear fashion, right? So that's what linspace does. It just creates a kind of linear spacing of values between the two that you specify, and you can also fix the number of points that you want. In this case, I somewhat arbitrarily chose 20. Then for fit intercept, the only options are true or false, so that's pretty easy. And then for tolerance, I'm using a linear space as well. This will go from 0.0001 to 0.01. Actually, let's make that 001. That's a little far, right? And again, I'll use 20 points between those two as well. And then finally, for the solver, there are more options for ridge regression. There are multiple solvers. I just decided to use SAG and least squares over here as just to illustrate the point. You could add more. You could also just leave this as auto. I think it actually chooses the best solver for you based on your data anyway, but I just wanted to illustrate the point with this. All right, so with our parameter grid set up, we then simply set up a new kind of estimator. This will result in an estimator, and I will talk to that in a second. But we use the GridSearch CV module over here. First, specify our base estimator, which is ridge over here, the ridge regressor with its random state of 42. We then specify the parameter grid over here as params, what we set up. So these are going to be the values that GridSearch is going to iterate over. It's going to iterate over all of them. And then our cross-validation splitter over here. I'm going to stick to the exact same CV splitter that we were using throughout. Now, to the point that I mentioned, basically, when we run this, or after we run this, GridSearch is going to turn into an estimator in and of itself. There is a setting in the GridSearch module over here called, I believe it's called refit over here. By default, it's true. What it does is after it goes through all the different combinations of your parameters, it'll basically take the parameters which got you the best score. In this case, again, we're using the default score of R squared. So whatever gives you the maximum R squared value, it'll take that and generate or use that to create an optimal model. You can then use it like you would use any other scikit-learn estimator. And you can even see it over here, we're calling .fit on top of it. You can also call .predict, and by default, it will use your best estimator or the best found combination of parameters. So you can kind of just use it in the rest of your workflow as if it was another one of these kind of estimator modules. Okay, all that out of the way, let's go ahead and run this. We are effectively going to iterate through this entire space. And actually, just as a quick exercise, how many different points on our grid are there? Basically, we have 20 over here. So this would then be 20 times the 2 for fit intercept. So that's 40 times 20 again, which gives us 800 times 2 again, which gives us 1,600. So if we were to do this manually, we would need 1,600 different ridge regressors to be set up and then iterate through those. Now, of course, you could be clever with your loop and do this anyway, or use like iter tools or something like that. But GridSearch makes it super convenient, right, to do. I literally don't have to think about any of that. I can just input my information into GridSearch CV and hit run on it. Okay, and we get a result after 33.8 seconds over here. So kind of long. I mean, with a ridge regressor, it's pretty fast to produce these kinds of models. If you were using a more complex model or using something like a neural network or any one of the kind of deep learning type models, this would take significantly longer, right? Because to train each one takes a while, whereas over here, the ridge regressor is really fast to train. Just something to mention, if you do want to speed up training, like I say, I mean, this isn't really a good use case for speeding up training. I mean, 30 seconds isn't bad, right? But if you really did want to speed up training, there is an option over here to specify n jobs. And what this is using is joblib under the hood. So basically you can train multiple or run this loop in parallel, basically. So if you specify, let's say, two jobs over here, it'll run two jobs in parallel. If you specify four, it'll run four jobs in parallel. But this is limited by how many jobs your specific CPU can handle. So just be aware of that. If you set n jobs to -1, I believe it'll use all CPU threads that it can, or take advantage of all your CPU cores, should I say. But that's just a neat way for you to kind of speed things up if you want to. But nonetheless, this is quite resource intensive to do. I mean, we had to go and create, or GridSearch had to go and create 1,600 different ridge regressors and apply the training, testing, and score producing across 5 different splits per those 1,600 different ridge regressors. So a lot of work being done, right? And if we take a look at this and open this up, we actually get the best estimator result at the bottom here, just because I'm printing this out, or leaving this .fit result over here, and it prints it out for us, saying that it got an alpha value of 5. So it immediately jumped up to the max alpha, right? Which kind of hints to me that we should probably increase our alpha value, right? Or our alpha search value by quite a bit if it's immediately jumping to the maximum we gave it. It's saying that fit intercept equals false is optimal as well, which is pretty interesting. I would not have expected that. Random state is fixed anyway. The solver that it used was SAG, and the tolerance it used was 0.000147, or about 0.0015 over here. So good to note, and interesting to see. Now, if we did want to print out all of our different results, basically get a hold of all of the different kind of combinations that were tried, how long the training took, what the scores were, that is available to us. So it's not just the best that gets returned. In this case, it did, show us the return value. And like I said, GridSearch now becomes an estimator that is working with the best set of parameters over here. But if we wanted to see all the results, we could effectively take our GridSearch over here. Let me just put this in the center. We could take our GridSearch and get the CV results over here. So let's take a look at the CV results. Now this prints out a dictionary that gives you every result that it has gone through. Now this is quite big, right? There's a lot of it, and you can already see that VS Code is like, well, you need to turn this into a scrollable element if you want to keep scrolling. So this gives you a dictionary basically of all the different results, but this is kind of hard to read. What is really nice though is that you can convert this to a data frame quite easily. Basically, it's set up in such a way that it works nicely with the Pandas data frame API by simply doing something like this, pd.dataframe, and I just kind of give it my gridsearch.cv results. And if I run that, it gives me a really nice looking data frame. Let's actually save this to a variable. So let's say like results, or actually let's say gs for GridSearch results. df equals this, and then go ahead and print this out. So gs results data frame. Let's just grab the top 5 values. Awesome. And so this kind of lays things out a little nicer. It kind of shows you the mean fit time, so the average time that it takes to fit, the standard deviation of it, the mean score time, so basically how long each one took, and then the different parameter combinations that it tried. So in this case, it tried 0.5 with the fit intercept being true, the solver is SAG, the tolerance is 0.001, then it's got all the params over here, and then the different test scores. So each split, basically each of your cross-validation splits, so it should have 5 over here, starting from 0, so our max split is 4, and then it gives you the average as well, the average test score, and its rank over here. So if we wanted to actually see all the details around the best the best model that it found, we could look for where rank equals 1. So let's do exactly that. Right, so over here, I'm just taking our GridSearch results data frame and then filtering where rank test score is equal to 1 to kind of get our values. And it looks like we have a tie between 3 different models, actually. So let's just see if I look at the mean test score. Yeah, they got the exact same score over here. What I suspect is probably that these have different tolerance values. Let's go ahead and validate that. Yeah, okay. So the tolerances are slightly different, but it looks like the solver is sag in each case, the fit intercept is false, and the alpha value is 5 in each case. So basically the only difference was the tolerance value used over here. Okay, so that is effectively how you would use GridSearch. You could also go ahead and save these results. If you wanted to keep these around, you could save them to CSV or write them to a database or that kind of thing. But you would have to go and actually write those modules. You could also go and take this data and do some meta-analysis, basically analyze this data itself, look at which trained the fastest or which gave you the kind of best results, or if the results kind of plateau at some point. But we'll go through that when we touch on Optuna, because that makes it actually really convenient to do exactly what I'm describing, as opposed to you having to kind of think through how to visualize this, etc. Anyway, before we jump into Optuna though, I wanted to also go over randomized search, or the practical application of randomized search CV, cross-validation over here. And this is super similar to the grid search. Now, as we discussed in the theory, the only difference here is that this is going to randomly select points in your parameters, right? So basically on your parameter setup, I've got pretty much the same setup. Yeah, this is the exact same setup over here. And this sets up our grid. But all randomized search CV is going to do is basically randomly select the different combinations over here and try them out. Now, the key difference is that this argument over here is called param distributions. When we use randomized search, it's no longer the param grid, it is param distributions over here, and I'll explain why it's called that in a second. But the other key difference is this n iter over here. So this determines how many iterations you want to run for. So you have control over how many times this actually goes and samples from your grid, whereas with GridSearch CV, it went over everything, right? This went over all of the different combinations. And actually, let's just validate our math here. This went over all 1,600 combinations. So if I take len of GS results, df, this produced, 1,600 different combinations, or went through each of those and produced a score for them. You are now in control of how many you actually get with this n iter over here. And we'll take a look at that when we actually get the results. Now, on the point around why this has param distributions rather than params, that is because you are able to actually not specify just a list of values for your parameters. Instead, you can specify a distribution in here. Maybe we should go through that. I'll go through the kind of this case that is exactly the same or identical to our GridSearch CV case, and then kind of show you if we were wanting to use a random distribution rather than a list of values, we can do that as well, or use that with randomized search. So I'm just going to run this with 100 iterations over here and basically see what we get. Okay, significantly faster, 2.1 seconds, right? And what did it find? So it looks like it found a pretty high alpha value as well. The fit intercept over here is false as well, so it found that too. And it looks like it's using the least squares solver, which is different to what we had prior. And the tolerance value 0.006, interestingly, so a little bit higher than what we had previously. Okay, let's actually save our random search results. This is exactly the same as with the grid search. Basically, we can say rs results here is equal to pd dot data frame, and then take our let's say random search dot cv results over here, and then let's go ahead and print this guy out. All right, and this gives us our various values. Now, what I am interested in is, firstly, let's take a look at how many returns we got. So we got exactly 100, right? As expected, 100 iterations, 100 results. Okay, what I'm actually interested in is what was the top performer over here. as a kind of different way to get a hold of what the best score was, we don't necessarily need to filter this data frame. We can also do something like this. We can say random search dot best score over here. And if we specify that, that got us 7856. So let's just compare that to what we got prior. And in this case, we got 7857. So slightly better on the grid search because we tried more combinations of values, but not like that much better, right? So random search saved us a lot of time and kind of got there, right? We could also kind of argue that we could have tried different kind of like alpha values or kind of adjusted our tolerances, and maybe, you know, it was distracting for it to have the solver options and the fit intercept options, like fix those and rather save your iterations for features that are important. We'll actually touch on feature importance as well when we talk about Optuna. But in this case, we got results pretty fast. The last thing I just want to demonstrate is that distribution point that I was talking about. Basically, instead of me having to list, I can have a probability distribution that it will sample to get values out of. So let's do that. Let me go up to where I was doing my imports. And what we need is from SciPy dot, I think it's from SciPy import, where is it, SciPy, just confirm this. It's SciPy.stats, right, so SciPy.stats import, I want the distribution half norm. Now, why I'm choosing half norm is because this will give us only positive values. A normal distribution will, you know, oftentimes have negative values or potentially have negative values. Even if you scale it all the way like to the right-hand side or across the kind of x-axis, you still have the potential of getting negative values. A half norm does not give you any negative values, and I do not have any parameters that will take negative values. So I want, you know, a distribution that basically feeds me only positives, hence the choice, right? Okay, cool. So now we have a distribution instead of a fixed list of values. And just to note, the reason I was using SciPy rather than NumPy is because SciPy has a module or a method called .rvs that generates random numbers, and scikit-learn expects that .rvs to be present if you use a distribution over here. So you do need to use SciPy distributions or write your own distribution with a .rvs method on it. It's a little technical, but I just wanted to note that in case you wanted to test this out with different distributions, the most convenient thing to do is just kind of use a distribution from SciPy directly. Okay, let's try this out with a half norm with a mean of 2 and a standard deviation of 1. Let's go ahead and run this. Okay, that returned really fast as well. And let's see what it got for us. Okay, it seems to be getting like roughly the same value anyway, but you know, nonetheless, pretty cool to see. Let's just see what it is. Okay, this should still be 100, yeah. Okay, not much improvement, but yeah, the point was more just to illustrate that you can use a random distribution. You could use something similar for tolerance or something like that. Now, grid search and random search are incredibly powerful. I think that they are amazing tools and are super, super impressive, right? Typically, you know, in most use cases, random search is the way to go. But if your problem space is small enough, or like, you know, you want to actually go through every single combination of parameters, grid search is awesome, right? But I want to move on to level 4, where we start using frameworks like Optuna. And this is the moment that I've been waiting for, right? I think this is so cool. So the next thought, or the next level up in this kind of chain of maturity in hyperparameter searching and tuning is, what if instead of searching the entire space or randomly searching it, we could instead follow an optimal path to find an extreme value? Now, this is the thought that I had when I was searching for something like Optuna, but Optuna has a whole bunch of other awesome features that really convinced me of using it and integrating it into my kind of daily workflow, right? Okay, so let's get through this. The first thing I want to do is actually import Optuna, right? And I'm also importing trial over here. Okay, so I've already done this, but you know, just for good luck, let's run it again. But I wanted to grab this trial type. It'll become obvious why I need that in a second. But this type is just important to me. I'm going to use it for type hinting, basically. Now, the first component that you need to provide Optuna, or the first thing that you should put together, is an objective function. So over here, I have defined an objective function. I've left out some values. We'll go through those together. But basically, your objective represents the experiment that you want to run. And each experiment is recorded as a trial over here, or recorded with a trial number over here. So this entire block of code should contain the experiment that you want to run over and over again. It should basically contain the contents of the loop that you want to use to test out different parameters. Now, the way that you can use the trial, or each trial, in the Optuna objective function is as follows. Basically, in the model part over here, I want to be able to suggest values for each of these hyperparameters that I want to tune. And so I'm going to leverage the trial given to us over here, so for each trial basically, and use that to select a value for each of these. And effectively, the syntax that you'd use is as follows. You take your trial object, trial dot suggest, and you have a bunch of options over here. You can either suggest a categorical value, suggest a discrete value from a uniform distribution, suggest a floating point number, an integer, a log uniform value, etc. Right? And what I want for alpha is to suggest a float. And all I need to do is first specify a name for this parameter. So I could name it something like, like ridge underscore alpha, but for, ridge underscore alpha like this, I could name it whatever I want. This is the name that it's going to return to me for the different trials. It'll kind of make sense when I actually print out the values that it returns when we actually run this thing. But for simplicity's sake, I'm just going to select the name alpha, so exactly the same as the parameter name over here. And I now can specify a low and a high point. So basically a range, like we were doing before with CV and random search, or sorry, grid search and random search. Basically, we are going to specify a low point. So I think we used 0.5, right, as our low point. And our high point is 5.0. And we can specify a step, like how big the step should be between these, but I'm going to leave that blank. And basically, Optuna will figure out how best to navigate this parameter space over here. All right, and now for fit intercepts, I want to do a trial.suggest categorical. So this is a categorical value. I'm just going to name it the same thing that it is named over here. So fit intercept, right? And then I give it a list of values. So that's my kind of choices option over here. So all I want to give it is true and false in this case. And then I'm going to go through and just kind of add the similar kind of setup to what we had with grid and random search for tolerance and solver. Tolerance is going to be a float. Solver will also be a categorical. Okay, let us actually just run this so that we have our objective function available to us. Now, the next component that Optuna needs is a study. Basically, a study is comprised of many trials, right? So your study is comprised of many experiments or trials that it's going to try out. So what I need to do is create a new variable. Let's call it study. Yeah, that's really creative, right? And we can use Optuna.createStudy over here. Now, I'm going to keep things pretty simple for now. We can basically play around with different settings over here, but I'm just going to keep it really straightforward. All I want to do is specify a direction over here. So a direction basically says, what direction do you want to find an extreme value for? So notice that our objective function over here returns the mean test R2 value, right? So this is, the typical kind of part of our experiment. We get our CV results. I then calculate the mean test R squared value and return that. So direction basically says, well, do you want to maximize R2 or do you want to minimize R2? And in our case, we want to maximize R2. We want the highest possible R squared coefficient. And so in that case, we can basically just say maximize. Simple as that, to say find the maxima of our return value. And I'll leave it at that for now for this. What we then need to do is basically take our study and say dot optimize, so optimize. And what do we want to optimize, we want to optimize our objective function. So we give it the objective function over here. We just kind of pass it straight through with no arguments. Optuna will handle passing it the trials. And then we specify how many trials we want, the number of trials, or n trials over here. So how many times do we want to iterate over here? I'm going to basically make this 100 like we had with the random search as well. And then there's a nice setting over here called show progress bar. And I'm going to set this to true. This is just a nice to have. Now, again, as with kind of grid search and with random search, they had an n jobs option. This guy in Optuna also has an n jobs option. By default, it's 1, so it runs one job at a time, but you can run multiple jobs in parallel if you want to. I'm going to leave this as 1. We're not dealing with any kind of heavy operations here, so 1 is fine. Now, before I hit run on this, I want to show you visually how Optuna is going to search for the best parameters to give us a maxima in the R squared value. Okay, coming back to our drawing over here, where we were mapping out how grid search and random search work, I also want to talk about how Optuna works and effectively how any kind of like optimization algorithm works out for this kind of problem, or works for this kind of problem. Basically, Optuna will also pick a random starting point. Let's say it chooses this guy over here, so that maps to this point, and finds here as the R squared value. What it will do then is evaluate which direction it should go in order to keep getting higher and higher maximums. In our case, we are looking for a maxima. If it was a minima, this would just be inverted, right? So this now judges which direction is the gradient going, and clearly it is this way. So maybe it chooses this point, a higher alpha value as well, and kind of sees that it gets here. And then it chooses this point, so it's now gone from here to here. It maybe chooses this point over here and maps a little higher and eventually lands on this point perhaps as well, and declares that as the maximum. Now, for both both Optuna and random search, both of these are controlled by n iterations. Basically, you specify how many times it needs to run this experiment to try and find a maxima, right? And this is effectively how Optuna works. It is a slightly more, I want to say, advanced solution to this problem, and works on kind of the theory of optimization, right? That deserves an entire video series, never mind one video, but it can use different optimization algorithms to search across a space for the optimal value. And that took about 3.9 seconds. Interestingly, it didn't show a new study created in memory with no name. Oh, yeah, okay. I didn't actually name this guy, but that's a different story. I'll come back to that. But effectively, it didn't print out my progress bar, which is a little annoying, but hey, okay. But it did print out the different trials. So it went through each trial, each experiment combination, and it basically finished, or shows what values it finished with. So these are the different R squared values, and prints out the various kind of values that it tried for our hyperparameters. So the alpha, fit intercept, the tolerance, the solver, etc., which is pretty cool to see. But really, what I want to see is what was the best trial, right? Or what was the best value that it found out of these 100 trials? And what we can do to find that is say study.best trial over here. So best trial basically prints out the trial that had the best R squared value, right? And it looks like it got to 785,699, so about 7,857, right? It also gives us a bunch of information. You know, it tells us which number the trial was. It got to there in trial 75. Basically the date time that it was run, etc. If I wanted a more kind of convenient output, I could also just say kind of best, let's say best value, and that'll give us the optimal score that it got. And then further, if I wanted the parameters as well, I could search through the best trial object, or I could just kind of say best params over here. And this gives us the parameters that were used to find the best value. So an alpha of 4.998, so it seems like it's also kind of just jumping to the high alpha values. We should probably increase those. the fact that fit intercept is false, the tolerance should be 0.000385, so like about 0004, and the solver should be SAG. Now, the cool part, or one of the cool features that Optuna has, is that it has a visualization module to it, where you can actually take a look at the values produced by your experiment or by your study. So what I am going to do is actually visualize the feature importances. So I want to see how important each feature is in determining the optimal R-squared score. And this just gives me a convenient way of visualizing that. So to do it, I can say Optuna.visualization over here and dot plot importances like that. And then we basically give it the study that we're working with. So I think this should work. Let's just take a look if that kind of prints out. I don't have Plotly installed. All right. Okay, so I installed Plotly and added it to the requirements file as well. And it seems to be working. I did have to restart the notebook and rerun everything, but that's okay. So now when I use Optuna.visualization.plotParamImportances, it shows us the importance or relative importance of each feature, right? Or each hyperparameter, should I say. In this case, it seems like fit intercept is like, has an importance of like 99%, which is insane. So that's interesting. Then it's alpha, tolerance, and then the solver that we use. Now to dig a little deeper in this, I also want to visualize the kind of, I want to say R-squared values that we get from the different solvers. I mean, the different fit intercept values. So it's either true or false. Let's see what the spread looks like. So to do that, I'm going to once again use Optuna.visualization.plot. And in this case, let's say plot contour. Yeah. Or sorry, I actually want to plot a slice. So what this is going to do is specify that I want basically a slice of our error space, right? So if we think about that three-dimensional plot, I'm looking for kind of a plane in it, and specifically I'm looking for a plane that represents the comparison between the fit intercept value and the R-squared value. So I will specify that I want to visualize my study, so study, and the params that I'm talking about, the only one that I'm keen on right now is the fit intercept one. So fit intercept, like that. So let's take a look at that. Okay, and it shows us the difference between having the fit intercept value set to true and the value set to false. Now, the color of the dots is important. The darker the color, the higher the trial. It just shows you kind of like as each trial evolves, where does it concentrate most of its efforts. And it seems like, yeah, a lot of its efforts are on false, like it tries true once in a while over here, but most of its efforts are on setting fit intercept to false over here. So this seems to be the right option. All right, now that is completely fine. What I think we should do though, or what I would typically do, right, is now that we know this, we can almost say we should fix the value of fit intercept to false and then see what happens to our other parameters, like tune those parameters. So it seems like, the spotlight is being shone on fit intercept, but now we've got a definite answer. Like we should definitely not fit an intercept and set this to false. And we should kind of just focus on the other parameters then and try and adjust those. All right, but this leads me onto another really cool feature of Optuna. Basically, I want to run another study right now, but I don't really want to lose the information that I just gathered, right? I don't want to lose all of this trial information. Well, I'm actually going to rewrite it, but you know what I mean. I don't want to lose my experiment so easily. What Optuna does, or what it lets you do, is it lets you store your trials and your studies, basically. So actually, it lets you store all of your studies in a relational database or in object storage like Amazon S3. I'm just going to use SQLite because it's really convenient to use on my local machine, but you could use any relational database to automatically store all of this. Now, technically speaking, you could do this for GridSearch and random search as well, but you would need to physically like write a function which takes your data and writes it to a database or to object storage, which isn't so bad, but Optuna can do this out of the box. So before I go ahead and modify our study, let's actually store our results. Now, the only change we need to make is when we create our study over here. So first things first, let us create a study name. So we need to name it. And I will call this something like AutoMPG. AutoMPG, let's go with underscores. So auto_MPG. Let's call it like wide search or something like that. Then specify the direction. That's fine. Then we need to give it storage as well. Where do we want to store this? And in the case of using SQLite, you can simply say SQLite // and I will just call my SQLite database Optuna studies. So not feeling super creative. Cool. And then I can specify load if exists equals true. And I'll show you what this does in a sec. So now what will happen is a new database will be created, a SQLite database, and it will store my trial results. So unfortunately, we didn't store the results of this trial over here, but we are going to go ahead and run this and store the results this time. Oh, and by the way, when I restarted my notebook, the progress bar actually showed up. So, and when I reran everything, it actually showed up. So that was kind of weird. Anyway, let's go ahead and run this again. Okay, so we have run the trials, this time storing the results. So it says here a new study was created in relational database with name AutoMPG wide search over here. And that has added a database over here, or a .db file called Optuna studies. Okay, so the point that I wanted to show around this load if exists part is now if I were to rerun this, so let's actually set number of trials to 50 just for demonstration. The trials will continue from where they left off. It will not restart from scratch. If I specify load if exists, it'll basically load the previous trials or the previous study and use that as a starting point to continue. So if I hit run, you'll see now we start off with trial 100 and go up to trial 149. So this is really useful because you don't lose any data. So if you want to just do a few trials or try something out to begin with, you can do that and then pick up from where you left off. This is also safe because, I don't know, if you're busy doing your Optuna studies and your machine gets struck by lightning, that sounds like the origin story of a superhero, data science man, who defeats villains with a probability of 78%. The jokes are just getting better on this channel, aren't they? What am I saying? Anyway, okay, so you basically don't lose the trial information if you store the results like this, and you can kind of load them up. Also, what's convenient is if you want to go ahead and review a study at a later point, like do visualizations for it, you can basically load a study using Optuna, which is really convenient. But let's go back to what we started with. Sorry, that was quite a tangent. But what I wanted to do was actually take fit intercept and fix this value, right? So let's fix this value over here and set it to false, basically fixing it to a single value and then focusing on our other hyperparameters, because for this one, it's clear that it should be false. And now what I need to do is actually rerun this objective function. So this objective function is now changed. I now need to create a new study. Let's call it AutoMPG, something like excluding intercept, something like that, right? And this is just so that we don't conflict with the previous values, because this study expects the parameters to contain a fit intercept option, whereas our new study will not. There is no fit intercept option happening over here. All right, so let's go ahead and run this. Oh man, I only did it with 50. I actually wanted to do it with 100. It's okay. I'll stick with 50 for now. Okay, so this happens to get the best value of 785,691. So really grasping for those decimal points at this point. That gets us the best value over there. And the best params of 4.99, tolerance, solver, least squares. And then if we look at the feature importances now, it seems like, yeah, alpha is super important, tolerance not so important, solver not that important either. Okay, and if we plot a slice this time, let's take a look at alpha. And it's clear with greater alpha values, so the R squared value gets better. Now, one more cool plot that I want to show is actually a plot of what I was trying to illustrate with my drawings, and that is a contour plot. So just a quick one. So Optuna dot visualization dot plot contour over here, and I want it to be for our study, and it should have the params equal to, firstly, let's do alpha versus tolerance, just like we had in the drawings. Let's go ahead and run this. And what this does is actually plots out the contours of our error surface with the various trials on top of it. So this is kind of the assumed error surface that it's dealing with. And these are the trials that basically that Optuna has mapped out. And these are the trials trying to find a maxima. And this is effectively a kind of like top-down view of our grid search, or the 3D plot, where on the z-axis you have the R squared value. And this shows you by color the R squared value. Darker means higher R squared. So up here, we're reaching a kind of plateau where we find a maximum value or a high value of R squared. So from this, it's clear that we need to concentrate our search around about here, right? Between about 3.5 to 5, and a tolerance kind of between like 0.00035 and 0.00550. Sorry, it's really hard to say. But basically, this gives us an idea of where we can concentrate our search. So we can go modify our study and rerun it with new kind of like parameter gaps. Basically, narrow down our search and repeat until we get to a model that we are happy with. Now, I'm not going to go and do that just for the sake of time. I'll leave that as an exercise to the viewer. So if you want to try that out, go ahead and narrow down the kind of search space and try again, plot out the values, see if you're happy with that, etc. Just as promised, I'm going to take you through a more advanced workflow, or kind of a workflow that I'm trying out with Optuna. Now that we've gone through the kind of basics and the setup and gone through the different levels of maturity, you're pretty familiar with what hyperparameters are and how to search through them using Optuna, using grid, and using random search. So I want to take you through a workflow that I'm trying out and just kind of testing out. So this is just like high level thought at this point. If you think of anything cool to do with Optuna, or have found anything awesome to do with Optuna, I'd love to hear about it in the comments, but this is basically where I'm at in terms of learning this framework. So what I have done is created a new notebook called More Advanced Workflow over here. And I'm going to import all of the modules that I need, and I'm just going to run you through this notebook. So first things first, we're going to import our data, basically do the exact same thing that we did before, just getting a hold of our data and cleaning it up, dropping the null values, etc. In this case, I'm going to do scaling a little differently, but for now, I'm just going to grab our clean data and use that. So the first thing is, as a first step in this workflow, it would be cool if we could try many different models all at once and see which one best suited our problem. So if we had an idea that we were dealing with a regression problem, it was like a linear regression problem, but we're not sure if it's ordinarily squares, or maybe we should use lasso, or maybe ridge is the best option. In that case, what I'm going to do is basically take a wide range of features. And again, this would come from your initial analysis of the data. You would determine different features or feature sets that you want to try out. But, let's take a pretty wide set of features over here. Then I go ahead and create a model dictionary over here. And this model dictionary basically takes a string and maps it to the actual scikit-learn module. So ridge maps to ridge regression, lasso maps to lasso regression, and OLS maps to ordinarily squares or linear regression over here in scikit-learn. So setting this object up, I can now use it as part of my objective function in Optuna. So I'm going to do the same kind of spiel as before, basically take our clean data and our selected features, copy them into values, have our cross-validation splitter set up over here. But I'm now going to have a specific objective function called model selection objective, pass it the trial, And then in here, I wanted to select or suggest a categorical called model type, and it needs to choose between ridge, lasso, or OLS. I then go and retrieve the model from the model dictionary, depending on Optuna's choice. And if it's ridge or lasso, I happen to know that both of these use alpha and tolerance, for example, whereas ordinary least squares does not. So if the model type is one of these, go and suggest an alpha value, go and suggest a tolerance, and then create a model instance where I use those suggested alpha and tolerance values along with a fixed random state to create a model instance. So this is for ridge or lasso, but in the case of ordinary least squares, I'm not going to add any kind of fancy hyperparameters to it. I'm just going to use vanilla linear regression over here. I then go and do my scaling over here. And, just for some fancy footwork, I'm using an sklearn pipeline. I'll go through pipelines in a completely different video. I think they're really cool, but basically they let you chain transformations together in scikit-learn. So I want to do scaling and then apply my model to the data. So apply the standard scalar and then apply the model to the data. Get our CV results, get our mean R-squared score, and return it, because this is still what I want to maximize with Optuna. Let's go ahead and run that. And over here, I'm creating a new study called AutoMPG Model Selection, maximizing this, and then using our Optuna studies database. I don't have a .db there. Yeah, that should be good. And I'm trying this out with 100 trials. So let's go ahead and run that. Alright, so we've got our results. We ran 100 different trials, so let's check the best parameters. Turns out that the optimal model type over here is ridge with an alpha value of 3 and a tolerance of 0.0004. And let's take a look at our best value. Okay, this is 895, so pretty good. And let's plot a slice over here. Use the Optuna visualization to plot a slice of the model type selection, because this is what I'm most interested in, right? And pretty much the the ultimate hyperparameter, which model we're using. And running this should give us a plot of our different options between ridge, lasso, and ordinary least squares. In this case, they actually look pretty close. I mean, ridge, although it's the best, is not that far off from ordinary least squares over here. And it turns out that lasso has got the widest spread. Even then, this is between 0.890 and 0.896. So a difference of 0.006 is what we're talking about here. But so each of these are doing pretty well relative to one another. Now, in real life, I'd actually probably choose ordinary least squares. It's like the simplest model, and really I'm trading off like tiny decimal amount of my R-squared value for simplicity. Like, I genuinely say, if this was the result, I'd say, hey guys, let's just use ordinary least squares. Like that 0.000 whatever R-squared amount is not worth us adding complexity to our model. But for the sake of this video, I will kind of just choose the best, that being ridge, and continue on with that. All right, so we've established that our model that we want to choose is ridge regression with about these parameters, right? But what if we tried different feature sets as well? Because a hyperparameter that we didn't talk so much about, I kind of briefly mentioned it, but is which feature set you're actually going to use. So in this case, we can set up different sets of features. For example, over here, I have the wide set, which has weight, cylinders, miles per gallon displacement, acceleration, a narrow set that just has 3 of them, and a moderate set that has 4 of them. Now, you could have multiple different feature sets, or try something like select k best or something like that from scikit-learn to establish feature sets. But in this case, I just wanted to show you that a hyperparameter that we can also play with is the features that we actually, or the predictors we actually feed to our model. So in this case, I'm just going to set up this dictionary. And now my objective function is going to fix the model that I'm using. So I'm only using ridge regression this time. I still want to explore my alpha value. And actually, you know what? At the same time, let's increase this, because I was dealing with 3, but maybe let's try 6 or something like that. And the tolerances and random state, that's fine. Over here, I'm just saying suggest a categorical called feature set name. And then go ahead and grab that actual feature set from our dictionary up here. And then use that in the X and Y, in the X predictors kind of set over here. So That's why I've brought these two into the objective function now, because these become dynamic, because I want to change our inputs basically. Then still applying the standard scalar, our usual routine over here, and grab the mean R squared value as the result of our experiment. So let's call this FS, or feature selection study. Create the study, name it something appropriate over here, and go ahead and run it with 100 trials again. Okay, we got our output, and it looks like our best params are an alpha of 3.6, right? With a tolerance of 0.002, and the feature set name is the wide set. So choosing the wider set of features, the best value we get is 8956. Like, not that much difference, to be honest with you. But let's take a look at the slice over here between these guys. And again, the difference here is actually like reasonably significant. The narrow set gives us about 84 as a 84% as an R squared coefficient or R squared score. But the moderate and wide set are super close, right? Like, that is not a lot of difference. And again, if this was real life, I would go for the simpler kind of set of data. The moderate set has less variables, albeit like one less variable, but that still reduces complexity. And I'm really not losing a lot of the kind of score over here by using the moderate set as opposed to the wide set. But again, for the sake of the video, we can say, hey, just go ahead and use the wide set or something like that, right? And then let's plot our parameter importances. Turns out features are the most influential by like a lot. And let's plot a contour between like tolerance and alpha. Why not? And our maxima is between tolerance and the alpha value is like sitting around about here. You can see there's like a big plateau over here. Like, there isn't a definite maxima sitting around here. So that's why feature set is like the ultimate determinant, is because it gets things more specific, whereas tolerance and alpha, it's pretty broad as to like where the maxima is over here. All right, and I think I kind of spoiled the surprise. This came up on screen earlier. As a challenge, I want to challenge you, dear viewer, to trying this out for yourself. You can go ahead and experiment with different scalars. So we experimented with different models, kind of chose that, experimented with different feature sets. Now we can like decide which feature set to use. Now it's like, well, what if you used the min-max scalar, or the standard scalar, or tried to model the data with no scalar at all to see if that made any difference to the scores. So that is my challenge to you, to go ahead and try this out. And this basically wraps things up quite nicely. This is effectively what I am working with as my kind of workflow with Optuna. As I figure things out with it, I'll maybe change and tweak things a bit. But for now, it's basically like, start high level, try a bunch of stuff, select the best, or like kind of look at the results, and then use that to determine the next step and try another study and really get into that finer detail with your models and be, I want to say, more confident with what you're producing. So to recap, we basically covered the different levels of maturity of hyperparameter fine-tuning, from basically not doing it at all to more systematic approaches like grid search, random search, and then all the way to what I personally think is the gold standard at this point, which is using a framework like Optuna to really bed down the best hyperparameters possible. I also want to bring back a point that I mentioned all the way at the beginning. Basically, you shouldn't do this type of, or use this type of technique as a catch-all. It shouldn't be a substitute for really rigorous analysis of your data. Again, we didn't go through that because that really wasn't the point of this video, but fancy techniques and tools are no substitute for understanding the data that you are working with. And your intuition is actually the ultimate tool. These tools and techniques can help you get to the next level, but you need a strong base and a strong understanding to work off of. So don't think that this kind of automates the job of data scientists or ML engineers. Basically, you need to work with the data first, get an idea of what's going on, and then that will better inform you on how to use these tools and frameworks. Now, if you are interested in more in-depth analysis of the data that we worked with and building that kind of strong foundation and those foundational skills, Then check out my longer videos on linear regression using the AutoMPG dataset, or my k-means clustering video on using a customer dataset. Both of these are really great. We work from the ground up, go through things step by step. This is kind of the next step after those two videos, so check them out if you do have the time. Thank you so much for watching. If you found this video valuable, please do consider giving it a like, subscribing to the channel, or joining the TrentDoesMath community today for more info on data science, data analysis, and data engineering. Thank you so much again for watching, and I will see you soon.